it was a pleasure for me to hear all these talks, and also including two quantumish talks, which will actually help me. One by Peter Domokos about the Hungarian Quantum Technology Initiative, and also this new Quantum Informatics National Laboratory. And also Alberto's talk will be very much related to what I'm saying. Actually, I will ask the same questions, but from a completely different angle. And actually, of course, in a 35-40 minute talks, it's completely impossible to give a deep introduction into quantum computing. So the GPU laboratory did last year in their series of modern scientific computing lecture series, together with me, we made a complete lecture series about quantum computing, where at least we could cover some of the ongoing things. And this year, Gergely had the idea that we might also have a satellite event for those who are interested in more in the deep or more advanced knowledge. So because of that, we decided that my talk should be more like a general talk about quantum computing and the current status of quantum computing on an overview type of talk, not too deep. And then there will be, of course, a talk by Dani Nagy from Wigner and Ericsson, who will talk in more detail about quantum machine learning that touches also on Alberto's talk a little bit. And tomorrow we have this event, this satellite event to the GPU days, right after, or almost right after the end of the GPU day. So we start at 1 p.m. You can register at that homepage, and I also give there like a little bit introduction to our organizations and other organizations that are teaching people quantum programming. This is Q World, and also we are involved in Q Hungary. And after that, there will be 3 proper talks. One will be a demo talk by Ákos Budai and András Pályi from the Technical University, where they show like the elements of a quantum programming language Qiskit, and they will also run an online accessible IBM quantum computer. And then there will be a talk from János Asbolt from also the Technical University / Wigner about Google's quantum supremacy experiment, and the talk also by András Guillén about new type of classical algorithms that actually were realized only after the quantum version was up. I mean, typically there is this Netflix algorithm that was actually shown that there is a quantum algorithm that is exponentially faster, and so that quantum is always exponentially faster in this respect, found actually a faster classical algorithm. So it's this type of quantum-inspired classical algorithm. So because of this, these will be like these 3 particular talks. If you are interested, just come. And right now, I'm only giving an overview, and the next talk in Dani will go a little bit deeper into quantum machine learning. So of course, you are all aware that there is a huge hype on about quantum computing. It's all in the news since, well, I would say maybe 2013 or 2014. And one of the biggest news was that I would say there were 2 big news. One was Google's supremacy experiment, which was actually, I mean, IBM is saying that it actually didn't show a supremacy. I will slightly mention it, and tomorrow Ashby will talk, János will talk more about this. And also the other one is those online accessible quantum computers. And of course, since there is this much buzz, of course, politicians are also talking about this. And these are actually 3 very important pictures, I think, that shows well the world situation. In one, there is Trudeau, and who is going to the Institute of Quantum Computing, IQC, in Canada, Waterloo. Actually, Canada invested heavily in quantum computing already 10 years ago. So they are very, very well off. And of course, he was super proud when he gave a talk then, like 2 years ago. And on the other hand, Europe, at least in making like many qubit quantum computers, are lagging behind. And this is also very interesting that now they are trying to catch up. So this is a picture of Angela Merkel, who actually made a decision, or the government of Merkel, of building together with IBM to join German IBM quantum computers. And beside that, Germany will build one more on its own. And there is also a European initiative, Open Supercube, beside that. And also, following the Trump joke of Gergely in the first talk, I also have to show the third one, which was Ivanka Trump's Twitter post, where she announced that quantum supremacy has been reached in a collaborative effort. Look at the order by the Trump administration, Google, and the University of California, Santa Barbara. Okay, so what is the structure of this talk? I will give you a very, very short physicist view on what quantum computers are, and perhaps what quantum computers are good for a little bit. Then I will give a little bit more deeper and perhaps not that conventional view about what the current stage of quantum computing is, although I would say it's still the main view what I'm going to tell you. And since there are many companies coming to this event, I also would like to stress that actually right now within quantum computing, there is a huge surge in collaboration between different fields of science and technology and companies and research institutes and universities, and I want to talk a little bit about that. And then the involvement of Hungary in quantum computing, although I will only slightly touch upon that because Péter Domokos already gave a pretty good overview of that. So, of course, if you're a physicist, you know that quantum physical and quantum chemical problems are intrinsically hard. I mean, if you want to like find the ground state of a molecule, with many atoms, many electrons, to do it like even numerically, explicitly, it's very, very hard. And what lies behind that actually of this intrinsic hardness is that it's basically the principle of superposition and something that basically follows from this is quantum entanglement. And what does this mean? This means that if we have some physical quantity, okay, say the magnetic dipole moment of an atom that can be nucleus that can point upwards or downwards, then in fact in a quantum mechanical state space, you can take the linear combination. So it actually always the state space is basically a linear space. It's so that's very different from our ordinary state space, which are usually like discrete. I should also mention this, that computer scientists, just from theoretical point of view, have actually almost come to similar mathematics when they describe something called like the linear logic, when logic was not like of discrete object, but also formed like a linear space, the truth contents of logical statements. And why is this a special issue? Well, in the case when you have one qubit, like 0 and 1, and as Peter mentioned, then you can take a superposition of those two in some way. It doesn't matter too much, but suppose you would have like 5 qubits. Then what will happen is that a state, at least a pure state of a physical system, can actually be described by a linear combination, complex linear combination of 2 to the 5 different objects. Like, of course, let's say, as I told you, that we are talking about the nucleus and let's say a quantized magnetic dipole moment of the nucleus that can be either upwards or downwards, and let's call the upwards 0, downwards 1. And then if you have 5 of them, then of course you have all the 2 to the 5 combinations, like 0, 0, 0, 0 is when all of them is up, and so on. 1, 0, 0, 0, 1 is down, the others are up, and so on. And and describing that state, you would need actually more or less 2 to the 5 complex numbers. And of course, it's still okay, not so many, but we know from the famous exponential wall picture that this gets really bad when you go to the 40s, 50s, 60s. So still, for example, here you can still depict, if you depict in billions, which you can still imagine in some way, how far you could go with let's say 2 to the 33. But when we go further and further away to 40s, 50s, 64, then it becomes very challenging to show this. For example, on this picture, if 1 would be 1 billion, that exponential wall. And that's also what is the moral of the legend about the inventor of chess. And actually there it plays very, very big role, this 64. It was very smartly chosen, because if chess would have been made of 32 squares, maybe the inventor could still get his prize, but it was unfortunately more, and he got killed. You remember the story. He asked only for a grain of rice on the first corner, then 2 on the second one, 4 on the next square, and doubled. And after 33, you have 512 giga of grains, but after that, you don't want to go. So, and actually those numbers like 40, 50, 60 comes up exactly when we are talking about quantum supremacy, about, for example, the Google experiment. So as I told you, you have to have those, if you have these 200 qubits, say 200 atoms with magnetic dipole moments either pointing up or down, you would never be able to store on a classical computer the generic state of 200 of these, so of 200 qubits. So that already shows that there is something difficult in simulating quantum physics. And of course, this was what was realized by Feynman. And I'm not giving the quote because also I'm a little bit tired of it, and so everybody is giving the famous quote of him. So in this talk from 1981, which also got into press in 1982, that damn it, nature is quantum mechanical. You need to simulate it quantum mechanically. Instead, I'm going to give another quote, which I think is a little bit deeper. How can you simulate the quantum mechanics? Can you do it with a new type of computer, a quantum computer? Here the word quantum computer appears for the first time as I know it. It's not a Turing machine, but a machine of a different kind. So from the physicist point of view, it came up as something natural, like if we could somehow make a quantum mechanical system to work to calculate for us, then we could simulate other quantum mechanical systems. But then came a surprise, exactly due because mathematicians took up the challenge, and computer scientists, and actually they also say that also some classical problems could be solved by quantum computers. And I don't want to dwell now too much into these classical or orthodox aspects of quantum computing. Just let me mention quickly 2 things. One is the famous Bernstein-Vazirani problem, which András will talk about more tomorrow. But it shows somehow the strength already of quantum computing. Namely, suppose that you have a secret bit string, which is contained in a mystery black box, and you are giving another bit string. And then what you are doing is that you are multiplying the first bit that you are putting in with the first bit of the secret string, and the second bit that you are putting in with the second string of the secret bit string, and so on. So like 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1. And you just add these modulo 2, and then give the output. And then this output you are giving out. And then you can ask, how many queries do you have to do to determine the secret bit string? And actually, obviously, as you would guess, you need n number of queries. Basically, you have to put in the bit string 1, 0, 0, 0, 0, then you get out as 0, the first secret bit, then 0, 1, 0, 0, 0, and then the next one you get out, and so on. And there is no better way. So the Bernstein-Vazirani algorithm, and András will talk about this, where you actually only need one shot for getting out the secret bit string. For the case of the Shor algorithm, it's another very orthodox quantum algorithm where you can actually show that you can use it also for other tasks quantum computers you could use. This was in like more than 10 years after Feynman's famous talk. As the best classical algorithm that factors composite number into prime is actually has to take exponential number of times in the, well, 2 to the n square root of n time, where n is the number of bit described by the, which we describe this big composite m number. So it takes exponential number of time, while the quantum algorithm takes only a polynomial number of time in the number of bits. Okay, so let's come to the title question. What is the current stage of quantum computing? Well, we have come a long way from Feynman. And actually since 2016, 2020, there has been like a commercial boom. Like it's of course a speculative boom, but many things have happened that, in particular, I would say an important thing has been that they are building bigger and bigger quantum computers in the number of qubits, and also the gates and the qubits are becoming less noisy. And so here you can see like before Feynman, there was only one proposal which was not about quantum computation, but how quantum mechanics could be an important asset for cryptography. It's Stefan Wiesner's quantum money proposal, which is basically very close to the Bennett-Brassard cryptography proposal, but on the quantum computing level, basically there was this Feynman's proposal, which was coming from physics, and then in '94 there was the Shor algorithm, a lot of classical algorithms. And then, of course, people realize that one has to, that the qubits will be noisy and one should do error correction. And now there is a scheme for quantum error correction, which is pioneered also by Google and, well, John Martinez, who was at that time at Google. And one more thing, which is very, very important, is the supremacy experiment, which I will talk about. So, I mean, there are many potential platforms for quantum computing. So when we are talking about qubits, one which is used by Google, IBM, and also many other companies like Rigetti are the superconducting transmon type of qubits. They have good scalability, rather good controllability and coherence times, although the crosstalk error are big. One that I should want to mention are trapped ions, which has also super good, even better coherence times, even better controllability. The big problem there is scalability, how you put in more and more trapped ions into one trap. Actually, what they want to do now is to have more and more traps, and they somehow, by a micro wave communication, they do coherent communication, so quantum communication between the traps, and try to entangle different traps like that. And one that I also want to mention is photonics. There also the coherence, if it's linear optics, is very good. The control is also very good. At the moment, scalability is not so good. However, it doesn't seem to be like a fundamental problem like in the case of trapped ions. Okay, so let's talk a little bit about the quantum supremacy experiment that János will talk a little bit more about. So this was done by well, actually by a 54-qubit quantum computer of Google, but one qubit didn't really work, so effectively it was a 53 qubits, where in a rectangular 2D shape, where they put after each other 20 layers. And actually, it was the algorithm what they showed. I mean, what does quantum supremacy mean? First of all, it means that you give a problem, and you can solve that problem in really in a way, you can solve that problem in a quantum mechanical way in our lifetime or very quickly, in such a way that the problem on a classical computer would take really long time. So they estimated that that this strange task, which was the following: take this particular quantum circuit and then measure the outcome of the quantum circuit. What do you get? Well, you get a machine that samples from 53 bits. So it gives samples like 111000. So numbers like that. So it samples with respect to some probability distribution that the quantum machine produced. Can you make such a classical algorithm that can actually describe, like, let's say in a Monte Carlo or in a different way, make a similar sampler? And the Google scientists, they said that you cannot, and with the best classical simulator, you would need 10,000 years. I have to first of all say something here, that basically the state that came out is not really the pure state that would have been produced by an error-free quantum computer. Instead, actually, it's a mixed state, and you can imagine the sampling in the following way. It's a mixed state, and it's like white noise up to 99.9%, and only this quantumness comes into as a 0.1%, this pure state sampling. So you can imagine that out of, like, this sampler makes the following thing, this quantum sampler, it sampled out of 1,000 experiments 999 times. Of course, you don't know when because it's probabilistic, from the white noise, like every string has equal probability, and only 0.1, like 1 out of 1,000 times, it samples according to probability distribution described by this circuit, or the pure state as an outcome of this circuit. And still, you cannot really simulate that classically. You would need, for such a sampler, it's still a very highly entangled state, by the way, interestingly, you would need a classical machine that would calculate it in 1,000 years. At least that's what they claimed, using a type of Schrödinger Feynman algorithm, or the Google scientists. Then IBM computer science suggested that maybe if you use some very tricky supercomputer in a very tricky way, could we go down to 2.5 days, but it's still unclear. Maybe they will at someday show it. On the other hand, I have to tell you that, I mean, if you go up to 60 qubits, then there will be no classical computer that can do. Of course, you can say that this task is not super interesting. And you might be right in that, but let me tell you something about this. So here, this probability distribution was not particularly interesting, but there are other ways of getting interesting probability distributions. For example, through bosonic quantum computing with a sampler called the boson sampling algorithm. There, the probability distribution could be obtained could be related to permanence of some matrices, and permanence of matrices are hard to calculate, and that has much more structure. And of course, if you want to do quantum machine learning, then one key ingredient in many machine learning algorithms is to produce some interesting probability distributions, or learn some interesting probability distributions. And in fact, this could maybe not be done that efficiently by a classical computer, as classical computers cannot really produce that many interesting or that many probability distributions efficiently than quantum computers. I will come back to this point a little bit. So what is Google's roadmap? Actually, this picture that I'm showing was presented first just a few months ago, 1.5, 2 months ago, in the academic symposium, or Google's academic partner symposium. But then they showed it also at other places. They tried to mimic John Fitzgerald Kennedy's approach to the moon, landing to the moon, who said that within the end of the decade, we will be in the moon. And that actually succeeded, that program. And what they want to do is that they want to build very similar to this. They want to build bigger and bigger superconducting quantum computers. And within the end of the decade, or before the end of the decade, 2029, they want to build 1 million qubit quantum computer. However, I have to say that these are physical qubits, and they will be noisy. So you can fight noise with something called error correction and do very perfect qubits. For that, with the good noise level, which is still not reached by the Google team, by the way, you could perhaps encode one logical qubit in 10 to the 3, so in 1,000 physical qubits. This would mean that 1 million physical qubits would amount to 10,000 logical qubits, but then they would be really stable logical qubits, so you could do any quantum operation. And actually just a few weeks after that, of course, IBM also produced their roadmap, and similarly, like Google said that in 2023, they will have already 1,000 qubits. That's what IBM also said, like 1,121. And they didn't put a date for the 1 million physical qubit one, but they just said and beyond, and they wrote 1 million qubits here. And if you go to PsiQuantum's homepage, you will see the same thing. It's a photonic quantum computing company, very successful. They also want to do, although they also don't put a date, build a machine with 1,000 qubits. And all the three are, of course, talking about fault-tolerant quantum computing. So using qubits that are protected against errors, and where the qubits can live very long and the gates are very good. But how can we reach that? Okay, so here you can see the number of physical qubits on the x-axis and the error rate of the two qubit gates, let's say 1 qubit and 2 qubit gates. And you can see that what they want to reach is this 10 to the 6 number of physical qubits, where you can actually do useful quantum computation, so quantum computation with 1,000 qubits with error correction. But we are still not there. We are still not exactly at even at 100. I mean, maybe next year there will be some companies coming out with 100 qubits, like Google promised that, for example, in 1,000. And although the error is small, it's not completely clear what kind of applications you can do. For sure, if you do quantum error correction, you will have too few qubits. And it's also unclear whether how long we will be in this shaded near-term application era, which is also sometimes called the noisy intermediate scale quantum device era, NISQ era. And if it's more than 10 years, we have to actually think about useful algorithms there. Okay. Okay. And if we think about useful algorithms in this current era, we have to like step away from those algorithms that I mentioned, like the Shor algorithm or these orthodox algorithms like a Grover search algorithm and the relatives. And we have to build algorithms for near-term quantum computing. And as I said, one of the best options for this is quantum machine learning. I mean, of course, you could first think about quantum machine learning that quantum computing is hype, machine learning is hype. You put them together, it's super hype. And it's also partially true, but also I would say that there is actually a deeper reason behind this. And the deeper reason behind this is the fact that right now what we can do is with quantum computers, better than with classical computers, is to produce samplers like probability distributions or samplers of probability distributions that you cannot produce those probability distributions by classical means. And thus you can learn using those in a better way. And in general, you can also perhaps do optimization in a better way. And both of these are related to variational or hybrid classical quantum computing, which has the following, which is illustrated in the following picture. Basically, what you are doing is that you are putting as much computational power to the classical computer as possible. What does that mean? So, for example, I go to the next stage. For example, suppose that this is a very typical algorithm, what I'm showing this, called the quantum approximate optimization algorithm. And here you might want to calculate the so-called max cut problem, which means select those edges, which select all those vertices in one group, such that if you cut out those vertices, then you have to cut edges with maximum weight if you add those weights on the edges. And such a problem, if you want to calculate such a problem, or the traveling salesman problem can be also formulated like that. It amounts to finding the ground state of basically of a classical Ising model, and there is this algorithm that tries to find this, called the QAOA algorithm, which starts from the so-called plus state, which is actually a linear combination of 0 plus 1. And if you take it in all of the qubits, what you get is uniform superpositions of all bit strings. And then apply up to some time gamma 1, first this Ising Hamiltonian, then you apply an X gate, which is basically flipping up to the X gate would be that it flips completely, but maybe you only want to flip according to some probability, like you make a small X rotation, so that you don't completely flip the spin. So with beta 1 parameter shows how much you flip coherently the spin. So if beta 1 is 0, you don't flip it at all. If it's pi, you flip it completely. And you apply after each other these gates, these unitary gates that you can decompose efficiently into 2-qubit and 1-qubit gates. And then maybe you get a good value for the or maybe a bad value. You can see what kind of ground state you get. So like you get a value for the optimization problem. And then with the classical optimizer, maybe using gradient decay or maybe some other method, optimize these parameters. So the classical computer has also to do a lot of things. And the hope is that you can actually use a path in the Hilbert space that you wouldn't have been able to do using classical optimization. So this is basically what variational computing is about for optimization problem. But you can also use this also for finding eigen states of complicated quantum Hamiltonians, and also for machine learning to produce very interesting probability distributions, for instance. So I would say that currently the best hope for quantum computing in the NISQ era would be, first of all, quantum chemistry and quantum physics using these variation algorithms, and similarly using variation algorithms, optimization, and machine learning. Factoring is not really in a NISQ era algorithm, but there have been serious improvements there as well, and there have been papers showing that it may be 8 million qubits you would be able to factor numbers that could break the RSA code. And of course, it's very important to have future ideas. And I will finish soon. of course, many people are claiming that now quantum computing can have effect on everything in quantum chemistry, quantum simulation, quantum application, quantum machine learning, and you can see pattern matching, protein folding, everything. And I mean, it's not true per se. However, I have to say that as the number of as the physical gate length in classical computers becomes smaller and smaller, I mean, quantum effects will be there inherently. So I mean, these classical computing paradigms will be in 10 years or maybe later, but it will be over up to, yeah, well, it could be over up to soon, and then quantum computing must be really taken seriously, even for those who are skeptical of this, because there is no way out of it. But to me, make a more positive ending of the thing of this talk, I would say that actually online accessible programmable quantum computers became democratized actually quantum computing a lot. I'm also using them. I'm finding out new error mitigation schemes than other people use, and also startups can use this. Of course, multinational companies themselves build those things. So this time is a very good entry point for virtually everyone who is interested and who believes in quantum computing, and there is great software for it. We are at Wigner also involved in trying to write good software for actually photonic quantum computation. And what is important in this current stage is this collaboration across disciplines and across the academic and also company landscape. I mean, there will always be some domain experts who are coming that they want to have a solution for their problem, for, let's say, telecommunication or something else. And then nowadays we have to talk about if they want to have a quantum solution with quantum information scientists, and then go even deeper, like which hardware we should use for that, because as I told you, different hardware has different merits. For example, if you are good with shallow circuits, but you need many qubits, then you should go with superconducting qubits. There are plenty of those quantum computers around, and they are building it. If you have to have deep circuits and you don't need that many qubits, let's say 100 qubits, but you need really deep circuits, many layers of 2-qubit gates, then you go with trapped ions and so on. So this is a great place. And of course, the premier workshop and conference for this is this Q2B since a few years. This is the Practical Quantum Computing Workshop, which also will be held this year. Now it will be online, where actually it's exactly about academia and companies discussing like which practical question can be solved in the near future by quantum computing. And maybe Peter already talked about this Hungarian quantum technology program. So I will not really talk about this too much. I'm just showing the partners. I don't know if you mentioned them. It's like we have here 3 academic partners, which is Wigner, the Technical University, and Ötvös University, and also the Energy Research Institute is also involved. And we have also industrial partners. In particular, I am, for example, collaborating a lot with Ericsson. Then also Nokia Bell Lab is a partner. Then Femtonics and Bonn, the company Bonn is also a nice partner. So I would like to end my talk with that. And I'm saying that if you want to have know more about more particular questions of quantum computing, about the supremacy experiments, about the demonstration of how to program IBM's quantum computers through the cloud, or about quantum-inspired classical algorithms, then please come to our site and sign up for this satellite event. Thanks a lot.
Okay, Cindy, thank you very much. And it was a very nice introductory and even deep talk. So, is there any question from outside? I cannot see in the chat. Anybody else? Somebody from here, locally?
So it's completely dark here. I have to turn on the light. Oh, sorry.
You are in the dark. Arpi would like to ask something. Arpi, please go ahead.
Yes, about Moore's law slowing down. I would like to ask if you know the reason. So is it a technical reason, or is it just because there is less money in it, because the present computers we are using do what we want for most of the people willing to pay for it, so they don't buy new ones?
So look, I mean, you can say that there is a commercial reason behind this Moore laws in general, how it evolved and how it goes. But I mean, if you look at the size of one single gate, I mean, it's so small. I just depicted them. I mean, the quantum effects are there, right? I mean, if you go even to a smaller region, how can you avoid it? Like, I mean, physically, that classical computing, the usual way to have definite bits and so on, that the quantum noise, I mean, if you can call it, it's for the classical computer scientists, noise is not present. How would you be able to avoid that? This is my question. Like, I'm asking this back. Do you want to build bigger devices?
What I was asking is, how far are we with the present computer from the quantum limit? So my feeling is that we are pretty far, because I mean, the present CPU is quite hot, so there are huge thermal noises, and still it works.
Yeah. Wait. Of course. I mean, look. I mean, the thermal noises are there, but if you go to smaller and smaller regimes, of course, the thermal noise will also you will also have issues with that. I mean, what I can show you are what I showed you here. Maybe I can share it again. Are the wait, how can I share it? Or the gate, how big this one gate is, or one wire here. I'm sharing it, sorry. So maybe you are far away, but how far away? I mean, would you say 10 years? I mean, here you can see physical gate length in nanometers. I mean, nanometer is already the scale where quantum effect starts to become relevant, right? So, I mean, they showed it what happens until 2030. Of course, you can also build bigger computers and make better software usage, everything like that. But I don't think like in our lifetime whether this can be avoided.
My question was more related to something short term, because what you're saying is that Moore's law has to slow down in whatever 2030, because we would reach something. Mm-hmm. But Moore's law already slowed down in the previous 10 years. And that's what I wanted to ask, if the reason was reaching some technological boundary, or just that there is not enough commercial incentive to develop faster computers, because our present computers pretty much do it what the average users want to do, so they are not buying new ones. And if we already reached that point, then so my question was this, that
so I don't know if I can give a very educated answer to this, because this was just like a small part of my talk, because I don't know what you can reach with technology, but for me it seems evident that this has to come in, and I would say it would be strange if there would be not enough incentive to make faster computers, financial incentives. For me, I would find it strange.